Get titration calculations continued here. We left off with what, diprotic acid titration? We're done. So yeah, that was one of the homework problems. I think number 25 or something like that. So that's with the buffers, but what we're going to look at now are titrations. Did I do monoprotic? Weak acid, weak base? Okay, we didn't do weak acid, weak base. Let's take a look at that. Weak acid, strong base. Did we do that already? Oh, okay. Sorry, I meant that. We haven't done weak acid, weak base. Weak acid, weak base is simultaneous, so I'll just mention it. But we aren't going to actually do any calculations with weak acid, weak base. Other than if it's a Henderson-Hasselbalch buffer, then we will. Okay, so what we're going to look at now is diprotic, weak acid, strong base. This is very common calculation that we do. The titration curve is going to have two equivalence points. First, and then a second. Oh, did we? Okay.
Yeah, as long as the solution isn't too dilute, solution addition is not required.
Well, that was with the. Yeah, that's a diprotic, but this we're going to just look at titrations in general. So even though we did some calculations with this, we're going to do some more calculations because there's some shortcuts I want to show you that we can do. So when we're looking at the pH titration curve here, we can recognize the first equivalence point. The first equivalence point is going to be the point of inflection here. That's what we call the first equivalence point. And so what happens in this, so there's certain points that I'm going to mark off here. One point is just the initial acid. And that's when we've added 0 milliliters. And so here we have our diprotic acid, which I'll just use a generic acid, H2A. If it's just H2A, this is an acid solution. This is a diprotic acid solution. So with the diprotic acid, we have Ka1, Ka2, and Kw. Those are all the hydronium ion contributors. But, you know, most likely, we're only going to need Ka1 for this calculation because Ka2, because of the common ion effect, and Kw are going to be very small. And so, unless Ka2 is pretty large, like 10 to the minus 2, then we really don't worry about it. And so we'll just do one ice table rather than 3 for this. It'll save you time in this calculation. So we have the initial, just the acid here, the starting point. Now, once we start adding sodium hydroxide, call this point the initial acid, then we'll start neutralizing some of the weak acid. When we neutralize the weak acid, we end up forming conjugate base. And so H2A plus sodium hydroxide is going to give us sodium, hydrogen, A plus water. Oops, sodium, water. All right, so this region is called buffer one. It's buffer one because I've only partially neutralized the acid. That means that the sodium hydroxide is my limiting reagent, and the H2A is my excess reagent. So if I partially neutralize that, then some of the acid is converted into its conjugate base. And so what I end up with is a weak acid and its conjugate base. A weak acid and its conjugate base is a buffer.
What is the H2A again?
H2A is a generic acid.
No, I mean, what does the excess stand for?
Oh, this is the excess reagent. This is the limiting reagent. And so since I'm going to have excess unreacted acid and the conjugate base, this is a buffer. What forms from this reaction is a buffer. And so this is why we call it buffer one or buffer region. These two. Now, eventually I'm going to add enough sodium hydroxide that I neutralize all the acid, H2A. And in other words, I'm going to have equal amounts, in this case, 1-to-1 molar ratio, and that will be the first equivalence point. So at the first equivalence point here, which I'll call 3, I'm just left with the salt and water. The salt is sodium hydrogen A, NaHA. So there's no more excess acid, there's no more sodium hydroxide. It's all reacted. Now, what do I have left over here? What I have left over is, this is called an amphoteric salt. It's an amphoteric salt because HA minus, when it collides with water, can either gain a proton or could lose a proton. If HA minus loses a proton, then we form H3O plus and A2 minus, and we call that Ka. This is the Ka for HA minus. If HA minus gains a proton, then what we form is H2A and OH minus. This is Kb for HA minus. So I do seem to recall that in some previous example, we had this situation where we had a Ka and a Kb equation, and we only had to do one or the other. I chose the Ka equation because it's a little bit more convenient. We get the pH, rather than the pOH. And then there's that one caveat that it really depends. If Kb is dominant, we should have done the Kb because hydroxide. But in this particular case,
You said at point 3, we no longer have H2A? Or?
yeah, we no longer have H2A. In other words, at the equivalence point, I have equal amounts of acid and base. So it's called a stoichiometric mixture, and so it's neutralized. And so I'm going to have just the right amounts of base and acid to produce salt and water. So all I'm left with is salt and water here. Well, if I have salt and water, then it's not a buffer, right? Because what I need is a weak acid and its conjugate base, or base and its conjugate acid. It's not a buffer, so what I got to do is I got to take the strongest acid and react it with the strongest base. Well, the strongest acid in this place is going to be HA minus, and the strongest base is going to be water. But the situation is, the strongest acid is HA minus, but HA minus can also act as a base. And in fact, HA minus is the strongest acid and the strongest base, but HA minus plus HA minus yields HA minus and HA minus. So earlier we had that scenario where we had a Ka and a Kb. And I could pick one or the other. Do you remember that? How about in this case? Can I just do one? I don't want to do both. Yeah, they're not describing the same equilibrium. You're right. When I look at this, it's not possible. The top one describes the equilibrium between HA minus and A2 minus. The bottom one describes the equilibrium between HA minus and H2A. They're not the same, so I have to do them. I have to do both of these. Now, I could try to do this stepwise, but stepwise will fail, actually, with this. And not only that, we have one more. Because I can't have any amount of hydroxide and any amount of hydronium. You know, if the hydroxide goes up, the hydronium must go down. And so these are going to be tied together with Kw. And so what I have to do is I have to solve these three, Ka, Kb, and Kw, simultaneously. Well, if you saw the, I did the homework Zoom for the simultaneous. That took a long time. But, that simultaneous was a lot easier than this simultaneous because that simultaneous only had 2 Ks that we had to solve simultaneously. This is 3 Ks that we have to solve simultaneously. And so, unfortunately, it's beyond the scope of this class. We're not going to solve 3 Ks simultaneously. Instead, somebody else did it. And so somebody else did the simultaneous and found out that this is a special case. This isn't an especially hard simultaneous because the special case is it's the same, HA minus in both of these, so it can be simplified in certain ways. And so if you do all the work of simultaneous, you end up with a simple equation. That is the pH is equal to the pKa. Did I already write this?
Plus the pKa, the conjugate base,
Okay.
divided by 2.
Divided by 2. Oh. Then I guess I was further ahead than I remember. Okay, so we can't do this simultaneously. We're in region 3 here. All right, so what we'll do is we'll do an example here of a specific calculation, then we'll look at the other regions here. But we're just going to look at the initial and the first equivalence point and the buffer 1 region, the buffer 1. Okay, instead of using a generic acid, we're going to use an acid. We're going to use .00 milliliters of oxalic acid. And this will be 0.100 molar oxalic acid. So what that means is this. If I titrate it, depends on what the concentration of sodium hydroxide I titrate it with. If I want to keep things really simple, I'm going to titrate it with the same concentration. So the oxalic acid is 0.100 molar, the sodium hydroxide is going to be 0.100 molar. And so this is going to make some of the calculations a little bit easier. So for example, to reach the first equivalence point, I have to add an equal amount of acid. Now your book likes to do millimoles. Sometimes I use millimoles, but most of the time I just do the solution-dilution method here. But in this case, let's do millimoles, just to take a quick look. When I take milliliters times molarity gives me millimoles. So this is 25 times 0.1 gives me 2.500. And this would be 2.500 millimoles of oxalic acid. At the equivalence point, I'm going to have an equal amount of base. And so to have an equal amount of base, I'm going to need 25 milliliters of sodium hydroxide. because 25 milliliters of sodium hydroxide will give me 2.5 millimoles, which will cancel that out. That's one way of thinking about it. The other way of thinking about it is this. If I have 25 milliliters of 0.100, then I'm going to need 25 milliliters of 0.100 to equal it. And so to hit the first equivalence point, this is going to be at 25.00 milliliters for this specific example. Now the book is going to have different scenarios that can pop up. Let's say, for example, I use 0.200 molar sodium hydroxide. So if the sodium hydroxide were twice as concentrated, would I use twice as much or half as much to neutralize? Yeah, I'd use half as much. So if this were 0.200 molar sodium hydroxide, then the equivalence point would be at 12.5 milliliters, not 25 milliliters. Does that make sense?
Is that because the acid is eliminated in that?
No, in this case, it's because the concentrations aren't the same, you know, and so the amounts aren't going to be simple. When the concentrations are the same, then the volume, you know, we can just use the volume as an indication of what it is. Now, the more tricky scenarios are like when they pick odd numbers. Like, for example, this could be 0.100, but they pick this one as 0.130. That's 0.130, then it, you know, the volume, so you have to sit there and calculate it using some stoichiometry. But I picked a really easy volume here, and so that's going to be a 25. So between 0 and 25 milliliters is the buffer region. Some of the buffer region points are very easy to determine. And so let me tell you what those are here. One of the points is the half equivalence point. And so where I neutralize 1/2 of my acid, well, the total acid is going to be 25 milliliters. And so to neutralize 1/2 of it, I'm going to need 12.5 milliliters. What I did in my green pen. And so the half equivalence point is going to come here. 1/2 equivalence point, and that's going to be at 12.5 to 468 milliliters. In titrations, we always go 2 decimal places in the volumes. Well, it's easy here. The pH is easy because the pH is equal to the pKa. So at the half equivalence point, pH is equal to pKa. There are other points that are pretty easy to get. One is the quarter equivalence point. 1/4 equivalence point. So if I've neutralized 1/4 of 25, what's 1/4 of 25? It's actually going to be, well, half of the half, which is going to be 6.25 milliliters. So my quarter equivalence point should come in at 6.25 milliliters, and the pH is somewhat easy here. The pH is equal to the pKa minus 0.477. So pKa minus 0.477. We also have the 3/4 equivalence point. The 3/4 equivalence point will come in at 3/4 of 25, which would be 6.25 beyond that. So that's going to be 18.75 milliliters. 18.75 milliliters, the pH is equal to the pKa plus 0.477, the pKa for oxalic acid. Well, yeah, I'm going to talk about that. It's actually really easy to figure out. I'll talk about that. How to get it. An odd one is going to be the 1/11th equivalence point. At least odd in terms of figuring out the volume, easy in terms of figuring out the pH. So if we're at the 1/11th equivalence point, how many milliliters is that? So what I do at the 1/11th equivalence point, I divide this into 11 parts. So if I take 25 and divide it into 11 parts, then one of those is the 1/11th equivalence point. Or I take 1/11 times 25. What is 1/11 times 25? Yeah, 1/11. It's 2.27. Yeah, okay, that's close. So 1/11th of 25 is 2.27 milliliters. The pH is really easy at the 1/11th equivalence point. Do you know what the pH is equal to? So in this case, at 2.27 milliliters, the pH is equal to the pKa minus 1. pKa minus 1. What about at the 10/11th equivalence point? So that will be here, running the room. But at the 10th, 11th equivalence point, can you guess what the pH is going to equal? Yeah, pKa plus 1. And so we can map out the buffer region quite quickly. Calculation. Now, where do these numbers come from? And so let's go through that. We'll do the half equivalence point first. So in the first example, let's go to the half equivalence point, which is 12.5 milliliters. So the half equivalence point. There's two calculations we can do here. We can do the long calc, and then we could do the shortcut, or we could just have it memorized. So this is not hard to memorize then. So let's do the long calculation first. And so for all the titration problems, we can do it exactly the same way. It's just sometimes we'd like to take shortcuts to speed things up. Here. But if we do it the same way, then the first step is always the same, which would be, let me get over here, which will be the step I, this preliminary initial step. Step I is what? Solution dilution. And so what we're doing is we're taking 12.5 milliliters of base and adding it to 25 milliliters of acid. And so for step I, what we're going to end up with is 12.5 plus 25 is going to be 37.5 milliliters of reaction mixture. So that would be the total volume. And so now what we'll have to do is we'll have to calculate the new concentration of sodium hydroxide. The new concentration of sodium hydroxide will be the dilution factor. The dilution factor is 12.5 over the total. And so the sodium hydroxide is diluted from 12.5 all the way to 37.5 in terms of volume. And so it was a 12.5 to 37.5 dilution of 0.100 molar. So what does that equal? This is going to give me 0.03333. I'll just carry 4 of them. It's just 215. But we're allowed 3 sig figs here. So I'll just carry 1 extra. Okay, the concentration of oxalic acid, the new concentration of oxalic acid, is going to equal, it's going to be 25.00 over 37.50 dilution of 0.100 molar. So this is twice as much. So this is going to be 0.0, go with quadruple 6 molar. I'm not going to round this. I'll only round it down. Okay, so this is my step I. After solution dilution, then we'll have our regular step 1. Which is really our second step here. After the solution dilution, we take the strongest acid and react it with the strongest base. So the strongest acid present will be oxalic acid. The strongest base will be sodium hydroxide. When this reacts, we're only going to neutralize the first hydrogen. The first hydrogen is the most acidic. And it will react first completely before the second hydrogen reacts. And so what will form here is sodium hydrogen oxalate and water. Salt and water. But this is a special salt because this is an amphoteric salt. It's not a basic salt. It's not a neutral salt. It's not an acidic salt. It's an amphoteric salt. But we're not going to worry about that yet because what we're going to do is we're just going to plug in the concentrations. The oxalic acid is going to be 0.0 quadruple 6. The sodium hydroxide will be 0.0 quadruple 3. And the sodium hydrogen oxalate 0, and water is pure liquid. Don't deal with that. Here, whenever we have a strong species, strong base, in this case, strong acid, strong electrolyte, K is very large. In fact, K for this is very, very large. Because strong base plus water is very large. And a strong base like this plus an acid that's much stronger than water, which oxalic is going to be very, very large. And so what that means is this is going to react to completion. So strong always react to completion. But it depends on what's the limiting reagent. Because sometimes they can't react to completion if they have the limiting reagent. In this case, what's the limiting reagent? The NaOH. And so we're going to lose all of it. And so this is going to be minus 0.03333, minus 0.03333, and plus 0.03333. And so at the end of this, I'm going to have 0.03333 molar oxalic acid, 0 molar sodium hydroxide, so there's no more strong species, 0.03333 molar sodium hydrogen oxalate. Okay, in a titration, what we can do is we can just repeat. So we see what's left over and just repeat. And so step 2 would be see what's left over and then take the strongest acid plus the strongest base again. And so the strongest acid remaining will be oxalic acid, but now the strongest base is not sodium hydroxide. We have no more sodium hydroxide left. And so we'll have to pick the next strongest base, which will be sodium hydrogen oxalate. But when we react oxalic acid with sodium hydrogen oxalate, what forms? In other words, we're reacting the acid with this conjugate base. What's going to form is the same thing. And so we've seen this scenario before, So since we've seen this scenario before, then we get the same thing, and therefore we have to take the oxalic acid and react it with the next strongest base, which would be water, which is going to be a Ka equation. But then we also have this sodium hydrogen oxalate, which is the base, the conjugate base in this particular reaction. And we'll have to react that with the next strongest acid, which will be water. And so we'll have a Ka for oxalic acid and a Kb for sodium hydrogen oxalate. Do we have to solve that simultaneously? It turns out we don't, because they describe the same equilibria. If we look at the Ka for oxalic acid, the Ka for oxalic acid describes the equilibrium between I'm going to get rid of the sodium. Sodium is a spectator here. So, in this case, well, actually, it just gives hydrogen and hydrogen oxide. So this describes the equilibrium between oxalic acid and hydrogen oxide on it. And then if I look at the Kb, because I also have hydrogen oxalate. And so if I look at the Kb for hydrogen oxalate, then this picks up a hydrogen, forms oxalic acid and hydroxide. And so this describes the equilibrium between hydrogen oxalate and oxalic. They describe the same equilibrium. And so I don't have to do both. Although this one's more complex because this is an amphoteric. And so really, I'm oversimplifying it. There are more steps. And so if I look at it from the perspective of the amphoteric, then I have more steps. But if I look at it in terms of this, then we recognize this as an HH buffer. See that? And so if it's an HH buffer, what's the acid? The acid is oxalic acid. What's the base? The base is sodium hydrogen oxalate. Well, how can I call that a base now? Isn't it amphoteric? No, it's no longer amphoteric. The reason this is no longer amphoteric is because now this has to be the base. This is a stronger acid. This cannot act as the acid. This cannot act as an acid because there's a much more powerful acid present. There's a much more powerful acid present than hydrogen oxalate. It will never act as the acid. Does that make sense? Or no? And so if we're left with an HH buffer, then we don't have to do an ice table. Anyway, we don't have to do Ka or Kb. I would have picked Ka because it's more convenient, but we don't even have to do that. The Henderson-Hasselbalch equation allows us to bypass the ice table entirely and just go straight to the pH. And the pH is going to equal the pKa for the acid, which is oxalic acid.
Why is it HH buffer? I thought HH buffer is only for weak acid and it's conflict.
Yeah, this is the weak acid here.
Oh, is it not strong acid?
No, oxalic acid is still weak. It's borderline strong. So if we look at the chart there, oxalic acid is at the top of the weak acids.
Sorry.
And then the border is at hydronium. Do you see? If we're below hydronium, it's considered weak. If we're above hydronium, it's considered strong. That's the border. And so this is a weak acid and it's conjugate base, and therefore pH is equal to pKa of oxalic acid plus the log of the base, which would be sodium is neutral, so it's just hydrogen oxalate, it's HC2O4 minus, over oxalic acid, H2C2O4. And then we can plug those in here. This is equal to the pKa plus the log of 0.0 quadruple 3 divided by 0.0 quadruple 3, which is the log of 1. The log base 10 of 1 is 0, so the pH is just equal to the pKa at this point. So we just have to figure out what pKa is. Okay, let's look at the shortcut method for determining this. Does a buffer solution depend on concentration? That is, if I make it a little bit more concentrated or if I make it a little bit more dilute, is that going to change the pH of the buffer solution? No. The buffer solution's pH just depends on the ratio. It doesn't actually depend on the magnitude of concentration. So So as long as I have the same ratio, I should have the same pH. And that holds unless I dilute it to an extreme. That is, it'll maintain that pH until I dilute it too much. When I dilute it too much, then it's no longer going to have the same pH. But 0.0333, it's concentrated enough. And 0.1, we consider that pretty concentrated. So it doesn't depend on this. So the shortcut method, I'm going to skip step 5. And I'm going to skip step 1. And I'm going to go straight to step 2. Step 2 would be the Henderson-Hasselbalch equation. And so we're going to go straight to the Henderson-Hasselbalch. The pH is equal to the pKa for that cell acid plus the log of this. Log of base to acid. When I look at this, how much of the acid was converted into base? Well, half of it. I started off with quadruple 6, I ended up with quadruple 3. Half of it was converted to base. And so over here, I'm going to say that half of my acid was converted into base. And that leaves how much acid left over? Well, the amount of acid that's left over is 1/2 the original amount. And so half of this was converted into base, the other half. Okay. So where this comes from here is this. If I were to look at the ice table at this point, this is the way I do visualize an ice table. I'm going to do this for a generic acid, H2A plus sodium hydroxide yields NaHA plus water. So just in general, for some generic acid, I start off with an initial concentration of C. And then I only have half the required concentration to neutralize it. Well, half the required concentration will be 1/2 C. And this will be 0 here. And so that means at the end of this, there's going to be a change. I'm going to lose half of that. So that's going to leave me with 1/2 C left over. This is going to be 0, and this is going to be 1/2 C. So this is my HH buffer. Okay. Where I've converted half of it to product, and I have half of it. So 1/2 over 1/2 is 1, and the log base 10 of 1 is 0, and therefore the pH is equal to pKa. So this would be, the bottom here would be C minus 1/2. The C is going on. All right, let's do the shortcut method for the 1/4 equivalence point. I'm going to go straight, because I'm in the bottom region, I'm just going to go straight to the Henderson-Hasselbalch equation. H is equal to pKa of oxalic acid plus the log. Now, how much of the acid has been converted to base? If I've neutralized 1/4 of the acid, how much has been converted to base? So it turns out 1/4 of it will have been converted to base. So this is the equivalence point here. If 1/4 of it has been converted, how much remains unreacted? 3/4. So it's 1/4 divided by 3/4. So what I'm going to do is invert and multiply. So this is equal to pKa plus the log of 1/3. What's the log of 1/3? Oh, it's the pKa minus 0.477. Log 1/3 is 0.477. Negative. So that's how I got this number here, pKa minus 0.477. That's the shortcut. We could do the long way too. The long way works fine, and we get the same answer. That goes for the 3/4 equivalence point. Let's do the 3/4 equivalence point next. So this is something we can do in the buffer region. So the pH is equal to pKa plus the log. So how much of the acid has been converted to base now? 3/4. And that means how much remains unreacted? 1/4. And so this is going to be the pKa plus the log of invert and multiply. 3 over 1 or 3. The log of 3 is plus 0.477. Let's hit 3 sig figs. It's actually, there's more. But 3 sig figs should be adequate for us. Okay, and let's go to the 1/11th equivalence point next. At the 1/11th equivalence point, I've added 2.27 milliliters of base, but I'm not going to do the solution dilution. I'm going to go straight to Henderson-Oswald. pH is equal to the pKa plus the log. Okay, so how much acid was converted to base? 1/11 of the total, which is 2.27 out of 25. How much remains unreacted? 10/11. And then we invert and multiply, and we get pKa plus the log of 1/10, or 10 to the minus 1. The power of 10 to the minus 1 is minus 1. And so we end up with pKa minus 1. At the 1/11 equivalence point. We can do the 10/11 equivalence point quite quickly. At the 10/11 equivalence point, we've used up, actually, how many milliliters? I didn't calculate that. Well, it's going to be 10 times this, so it's going to be 22.70. So 22.70 milliliters. What is the pH? So the pH is equal to pKa plus the log. Okay, if I've neutralized 10/11 of my acid, then that's all converted to base. So I have 10/11 base, and then how much remains? Only 1/11 remains. Invert and multiply. This gives us pKa plus the log of 1. Or no, not log of 1, log of 10. Log of 10 is just 1. So we have pKa plus 1. All right, so some things to be aware of is, the volume. It depends on what the volume here is. If it were 10 milliliters, we'd have to adjust the volumes accordingly. Like the half equivalence point would be 5 if this were 10. The 1/4 would be 2.5. It'd be a little bit easier. The 1/11 is actually 0.9. 1/10 of 10 is 1, so it's a little less than 1. All right, but that's just these, the 1/11, 1/4, 1/2, 3/4, 10/11. What if I didn't want any of those? In other words, pick any volume here between 0 and 25 milliliters. What volume? 1. 14.5 milliliters. Okay, so if I want 14.5 milliliters, I can do the shortcut way or I could do the long way. The long way would just be solution dilution, et cetera, et cetera. The shortcut method would be this. I just go straight to the Henderson-Hasselbalch. pH is equal to pKa plus log of. All right, so how much have I neutralized? I've neutralized 14.5 out of 25 parts. And so I've neutralized 14.5 out of 25 parts. That means how much is left unreacted? Oh, 10.5? 10.5 out of 25 is left unreacted. And so this is going to equal to pKa plus the log of 14.5 over 10.5. The 25's cancel. And so what is the log of that? So take the log of 14.5 divided by 10.5. So the pH at that point is equal to the pKa plus 0.1401 So 14.5 is a little after the half equivalence point here. It's gone. It's still fairly flat. It doesn't change a huge amount. All right, so I could do the same with any point. What I do is I figure out what is the equivalence point. And the equivalence point is I look at the total number of parts, 25, and I look how far I've gone here. And so this is the equivalence point here. This is the initial, which was initially we had 25 out of 25 parts of acid minus the change here. Okay. The next thing we want to do is this. We could figure out what the pH is at any volume throughout here. But what I want to do is I want to figure out what volume it takes to reach a certain pH. In order to do that, I have to make sure I know where I'm at in the titration. And so, for example, I need to know I'm in the buffer 1 region. In order to know if I'm in the buffer 1 region, I'm going to go ahead and calculate the equivalence point here because I don't want to go higher than the equivalence point because that will throw me into what we call the buffer 2 region. And calculations are a little bit different there. And so what is the pH of the amphoteric salt? So our amphoteric salt is going to be sodium hydrogen oxalate. Now, normally we do solution dilution, but do we have to do solution dilution for an amphoteric salt? No, because for an amphoteric salt, we don't need the concentration. The pH is just equal to the pKa of the amphoteric salt, which would be HC2O4 minus, plus the pKa for the conjugate acid. What's the conjugate acid of HC2O4 minus?
H2C2O4.
Yeah, H2C2O4 divided by 2. So I'm just going to use the values up there. What's the Ka for hydrogen oxalate? It's on the top right. Okay, so this will be the negative log of 6.4 times 10 to the minus 5. That's going to be the power of pKa. And the pKa will be the negative log of that. So let's take the log of 6.4 times 10 to the minus 5. 4.1938. .1938 pKa. All right, let's take a look at the Ka for H2C2O4. The Ka for H2C2O4 is 5.9 times 10 to the minus 2. So this is the negative log of 5.9 times 10 to the minus 2. 10 to the minus 2, that's fairly big. So that's really strong. Log of 5.9 is 10 to the minus 2. Comes out to 1.2291. So if I take 1.2291 plus 4.1938 equals divided by 2, that gives me a pH of 1.4823. That can't be right. Let me redo that calculation. Oh, maybe it is right. Let's see. Seems a little small. 4.1938 plus 1.2291 equals divided by 2. Yeah, this seems more reasonable. 2.7115. And so the pH at this point here is 2.7115. That would be the pH. So if I'm at a pH of 3, that means I'm in the next region over here. But if I'm at a pH below 2.7115 and above whatever the initial pH is, then I'm in buffer 1 region. And so let's pick a pH in that region here. And so the next example will be this. Let's pick a pH of 2.50. So in order to hit a pH of 2.50, how many milliliters of sodium hydroxide do I need to add? Well, I'm in the buffer region. Since I'm in the buffer region, I'm just going to go ahead and use the Henderson-Hausbach equation. That is, pH is equal to the pKa plus the log. I know what the pH is, and I know what the pKa is. The pKa we just calculated. pKa for oxalic acid is 1.2291. So this is 2.50 equals 1.2291 plus the log of this ratio, which I'll just call the base to acid ratio right now. And so let's figure out what the base to acid ratio is. The base in this case is hydrogen oxalate, and the acid is oxalic acid. So doing that, I have 2.5 minus 1.2291 equals, and then I'll take the anti-log of that.
You're asking how many milliliters of the oxalic acid do you need?
No, we still have 25 milliliters of oxalic acid. What I'm asking is how many milliliters of base do I need? You know, where on this titration am I?
Oh,
This comes out to 18.659. Or we can say 18.659 parts of base to every 1 part of acid. 18.659 to 1. Is that the equivalence point? No. That's actually where we are here. This is the base to acid ratio. 14.5 parts of base, 10.5 parts of acid. So we have 18.659 parts of base and 1 part of acid. And the question is, how many total parts are there here? So if I have 14.5 parts of base and 10.5 parts of acid, how many total parts do I have? Yeah, the answer is 25 total parts. Out of those 25 total parts, 14.5 out of the 25 are base, and 10.5 out of the 25 are acid. And so the same thing goes here. I know how many parts of base I have, and I know how many parts of acid I have. What's the total number of parts here? Yes. And so what we have here is 18.65 out of the 19.65 total parts is base, and 1 out of those 19.65 total parts is acid. So I only have 1 out of 19.65 left over.
Where did we get the 18.65?
Oh, I just did 2.5 minus 1.2291, and then took the anti-log of that.
Oh.
So I'm solving for this ratio here. And so this came out 2.5 minus 1.229 is equal to 1.271. 1.271, which is equal to the log of the base to acid ratio. And then solving for the base to acid ratio. Once I solve for the base to acid ratio, what do I do? Well, I got 18.659. What I do is, this is parts of base, and the numerator is parts of base, and the denominator is parts of acid. The parts of acid must be 1. So it's 18.659 to 1. And then I want to figure out how much, what fraction of the acid reacted. In order to do that, I need to figure out the total parts. The total parts are the parts of base plus the parts of acid. That gives you the total parts. The same thing over here. The total parts of the parts of acid plus the parts of base. So the total parts are 25. And so what I can do is I can get a fraction, how much reacted. And so this is what I did over here. The total parts are 19.659. I just add these two parts together, the numerator and the denominator. And then the base is 18.65 out of the 19.65 parts that reacted. And the acid is 1 out of 19.65 parts that reacted. And so what we end up here is this. This fraction here is how much of the original acid reacted. 18.65 out of 19.65. So 19.65 parts would be all of it. That would be 25 milliliters. And so to figure out the volume, well, this is what we call the equivalence point here. To figure out the volume, we'll just take that equivalence point, 18.65 out of 19.65 times 25.00 milliliters. And it comes out to 23.728 milliliters. 23.728 milliliters, or 23.73 milliliters. And so the equivalence point is a fraction of what reacted. So if I reacted all of it, 25 out of 25, I'm at the first equivalence point. 3/4 of it, 1875 out of 25, 3/4 equivalence point. Half of it, 12.5 out of 25, the half.
So it's 23.73 milliliters of what exactly?
Of sodium hydroxide. Okay, so in other words, if I get to 23.73 milliliters, the pH will hit 2.50 here. So that's what we did there. Does that make sense?
What we're solving for
All right. Once we go above 25 milliliters and below, where does the second equivalence point come in? How many milliliters of base will we have at the second equivalence point? 50. Okay, that's correct. So when we hit the second equivalence point, we'll be at 50.00 milliliters. And so between 25 and 50 milliliters.
Sorry, I'm lost. From the equivalence point, where did we get the 19.65 from? So I'm like trying to catch up, so I'm lost right now.
Okay. Well, we got the base to acid ratio.
Right. That was 18.65.
Yeah, 18.659. Now, what does that mean? That means we have 18.659 parts of base to every 1 part of acid. But what we want to do is we want to figure out what fraction of the total have we neutralized. Have we neutralized 100% of it? 3/4? 75%? 1/2? 50%? What fraction of this did we neutralize? In order to figure out the fraction, we need to know how many total parts there are. So if I have 18.659 parts of base and 1 part of acid, how many total parts are there? In other words, here, this might be a little easier. If I have 12.5 parts of base and 12.5 parts of acid, what fraction? So we'll step back here at the half equivalence point. At the half equivalence point, we have this pH is equal to Ka plus the log of 12.5 to 12.5. So if I have 12.5 parts of base and 12.5 parts of acid, then I have equal amounts of base and acid. What fraction of the acid has reacted? Half of it. But wait a minute, isn't it 100% because this is 12.5 parts out of 12.5 parts? No, it's not 100% because this is base, this is acid. And we have to go back to the ice table to see. And so what we need to recognize is this is equal to 12.5 out of the total. How many total parts are there? Yeah, so 12.5 out of the 25 are base, and 12.5 out of the 25 are acid. Now 25 is the total, so this is the fraction that reacted. The fraction that reacted is called the equivalence point. And so this would be the half equivalence point because half of the total has reacted. And so all we're doing is we're doing the same thing here, except the numbers aren't so clean and nice. Now we take 19.65 parts out of 19.65 parts will be 25 milliliters. That's the total. And so I've almost neutralized all of it. Once I hit 1965 out of 1965, there's no more acid left, right? And so here I've neutralized 18.65 parts out of the total 19.65. This is not milliliters, this is just a fraction of what I neutralized. Does that make sense? Okay. Okay, let me, since this is getting crowded here, let me erase buffer 1 here. And let's take a look at buffer 2. This will be region 4, which we call buffer 2. The reason it's called buffer 2 is once we've neutralized all the oxalic acid, the only thing that's left over is sodium hydrogen oxalate, which is the conjugate base. But now if we continue adding sodium hydroxide, this can, converts to the strongest acid. And so the reaction here is sodium hydrogen oxalate, A being just some generic, plus sodium hydroxide is going to yield Na2A plus water. Well, we have going from point 3 here, which is the first equivalence point, to point 5 here, which is the second equivalence point. We're just partially neutralizing the acid. And so the limiting reagent will be the sodium hydroxide, that's our LR. This will be our excess reagent. And so if we consume all the sodium hydroxide, we're going to be left with an HH buffer, that is sodium hydrogen oxalate and sodium oxalate buffer system. And so this is the buffer here. So what volume of sodium hydroxide does the half equivalence point come in at? So I want the half equivalence point here, the second half equivalence point. What volume is that? Would it be half of 50, which is 25 milliliters? It can't be 25 milliliters because this is 25 milliliters here, the first equivalence point. So it's not half of 50. What is it? 37.5? 37.5 is correct. 37.5 because we have to divide this up. And so the first equivalence point is going to take 25 milliliters. The second equivalence point is going to take another 25 milliliters. But it's offset. The first equivalence point is referenced to 0 here. And so, however, the second equivalence point is referenced to 25. We're not starting at 0, we're starting at 25 and then adding another 25 to this. And so the second half equivalence point is going to be at 37.5 milliliters. And what is pH there? pKa2. That would be the pH. And so we can pretty much do the same thing for these, except we have to factor in the offset. which complicates the calculation a little bit. Yeah. All right, so the same thing goes. The 3/4 equivalence point would be pKa plus 0.477. The 10/11 equivalence point, the, actually, what would the volume be at the 10/11 equivalence point here? Which gives us a pH equal to pKa plus 1.
I think we said that before.
In other words, let me ask you this. Would I take 10/11 of 50 milliliters, or would I take 10/11 of 25 milliliters? If I want the 10/11, I want the volume here at the 10/11 equivalence point. Should I take 10/11 of 25 milliliters, or should I take 10/11 of 50 milliliters? No, I have to take 10/11 of 25. And what I do here is I'm not starting at 0. So what I'm going to do is I'm going to take 10/11 of 25, which is 2.7, or no, 22.7, right? And then add that to 25. So it's going to come out to, well, what is 10/11 of 25? 47.7? Okay. 47.73 milliliters will be pKa plus 1. Will be the pH. And so at the second buffer region, it's a bit more complicated because we aren't starting at 0. We're starting at 25. So all the volumes that we calculate are based on this second interval here, which goes from here to here, 25 to 50, which is 25 milliliter interval. Both of these have to be the same. So let's do a couple of calculations. Just one is pick any volume between 25 and 50. What volume do you want to know the pH of? 32? Okay. Okay, the first thing is we have to know enough of the curve to know that 32 milliliters will be in the second buffer region. 32 milliliters was in the second buffer region. How far into the second buffer region is this? The second buffer or buffer 2? But we aren't 32 milliliters into the buffer region 2. How many milliliters are we into buffer region 2? Well, buffer region 2 doesn't start until 25. So at 25, we just hit it. And so that means we're going to be in 32.00 minus 25.00. This is because it's offset, which means that we're 12.00 milliliters into buffer 2. Right? Oh, 7. 7.00 milliliters into buffer 2. Is that right? Okay. Well, if we're 7 milliliters, well, how long is it? Well, it's 25 milliliters. And we've only done 7 out of 25. If we've only traveled 7 out of 25 parts, then the pH is equal to pKa plus the log of, well, that's going to be converted into base. So it's going to be 7 out of 25. It's converted into base. How many more milliliters do we have left? Well, if we've only done 7, then we're going to have 18 milliliters left. And so that's going to be 18 out of 25 left to go. And so this is just going to be pH is equal to pKa plus the log of 7/18. 7 parts of base, 18 parts of acid. So log of 7 divided by 18, 2.21. So this is pKa minus all right.
Not negative 0.41.
Yeah, that sounds more correct. I got the wrong answer. Negative 1. So what was the pKa? Well, which pKa do I use now? Yeah, I have to use pKa2 because I'm now on this acid here. So there's something strange about the way we name pKa's and pKa's. So let me talk about that briefly over here. So oxalic acid is a diprotic acid. So there's going to be Ka1 of oxalic acid, which is the 5.9 times 10 to the minus 5. Or minus 2. And then we're going to have the Ka2 for oxalic acid. Ka2 for oxalic acid is just Ka for hydrogen oxalate. And Ka for hydrogen oxalate is 6.4 times 10 to the minus 5. So the same thing holds for the pKa. And so we could have pKa1, which came out to 1.229, was it? Something like that. And then we're going to have pKa2 for oxalic acid. pKa2 was the 4 point whatever. pKa2 for oxalic acid is just equal to pKa for hydrogen oxalate. So these are for oxalic. So over here, we use the pKa for hydrogen oxalate and not oxalic acid. That was 4 point something. Okay? All right, then the other example is pick any volume between 25 and 50. What volume do you want to do? Any volume between 25 and 50. Oh, actually, maybe we'll not do that. So we did that already. Sorry. We did it. We picked 32. We could pick any other volume. The calculation is going to be just the same. Let's pick pH now. So the pH in the second buffer region is going to be bound by 2.7115 on the low end. And then at the high end, what do we have? Well, at the second equivalence point, we've neutralized all the acid and we've reacted all the base. And so all we're left over with is the salt and water. The salt here, this is not an amphoteric salt. This is a dibasic base. It's A2 minus. A2 minus has a Kb1, this is A2 minus plus water, and a Kb2, which is HA minus plus water, which yields more hydroxide, and a Kw. Here, we don't have to do these simultaneously, we can do stepwise, I think. Let's look at the Kb's just to make sure. I'd like to just to do one step. This is just a base solution like we saw in chapter 16. But I need the Kb values. So what is Kb1? Well, Kb1 of A2 minus, actually, let's do oxalate in this case. So this will be Kb1 of oxalate, C2O4 2 minus, is equal to what? Well, the Kb, there's no Kb values with this in the chart. So what we're going to have to do is it's going to be Kw over the Ka for what acid? Not oxalic acid, but hydrogen oxalate. That would be the conjugate acid. The conjugate acid, we only need one hydrogen at a time, not both. Well, Ka for hydrogen oxalate is the same thing as Ka2 for oxalic acid. And so you could either use Ka2 for oxalic acid or Ka for hydrogen oxalate, they're the same. And so Kw is 1.0 times 10 to the negative 14. And then the Ka for hydrogen oxalate is 5.9 times 10, no, sorry, 6.4 times 10 to the minus 5. 6.4 times 10 to the minus 5. Okay, this is going to give us a Kb value of 1.5625 times 10 to the minus 10. Is that, what do you consider that? Weak? Moderate? Strong? Weak. It's pretty weak. Let's figure out what Kb2. Kb2 for, okay. We'll have to do that next time.